Okay, welcome you all for the first session on NumPy. What I want to do, maybe few more classes we will take to explore what are the key features that you should know when you are programming in using NumPy library, because both in data sciences as well as in AI we will be using this library in detail. Even TensorFlow uses this in the background. So having a clear idea of what is NumPy, how is it implemented, and what are the best ways to use them is very important for you to write an efficient, correct, highly performing code. Okay, if it has to be performing to the best of its ability, you have to know the inner details of NumPy. I will try to do my best to show you some intricate things which are hidden inside NumPy. So let me start with few things which are very unique compared to what is being done in Python, and why did they come up with a separate library for numerical computation as NumPy. That's the focus of this lecture going to be, and I will show you some sample code, a simple code we'll write, and then we'll see how it really differs from Python. So NumPy is a short form of numerical Python, a fundamental package for scientific computing in Python. So we need to use this in Python. It's a library for creating multi-dimensional array objects, and there are some derived objects also which you can create, which are called matrices or masked arrays. I'll talk about masked arrays maybe down the line. If you're already aware, it's okay. Otherwise, we will just touch upon that. And then it has got many routines which are operating on arrays, and then they do it a much better operation on arrays than what Python does. And the scientific Python package is an extension of NumPy, which also has lots of algorithms already implemented. So if you are to use them, you can just use those library functions and write your own applications. Now, what are the other mathematical functions supported here? Logical operations, also a lot of trigonometric, multiplication, vector, multiplication, matrix, all those things are done. You can manipulate data shape. Shape means the dimensions of the data. We can do sorting and selecting on existing data set. DFT, which is very popular in image processing, those libraries are there. And of course, both in AI as well as in DS, data sciences, linear algebra and statistical operations are very important. And we can also do a lot of random simulation, random functions are there. There are many more. Okay, so I'm not giving you the complete list, but these are all the things which NumPy supports. Now, let us understand how does the NumPy arrays differ from a normal Python sequence. At the core, NumPy is a package that supports ND array, the n-dimensional array objects. Now, what is ND array? ND array is a class. So, it's a type of n-dimensional array class which is used for creating arrays of that type. So, what you create is an array of NP, and you can pass a list which is like Python list, and it converts it into an NumPy array. Now, one important restriction here is that all the elements in an array should be of same type. I'm sure you must be aware of it. So ND array is a class and NP array is a method to create a ND array object. Now it encapsulates n-dimensional arrays of homogeneous data type. That means the data type has to be same, all the elements of same data type, with all the operations being performed with a compiled code for better performance. So now what I mean by compiled code here is all the library functions of NumPy are implemented as C functions. It's all implemented in C for efficiency as well as for quick operations. Now, We have done already in the last Python class how to interface a C code with the Python library, Python code. So same thing they have done to implement the NumPy completely in C, and they, when they are passing it to the thing, all the data whatever is there in the Python world is converted into C world, and then C functions do the job. Now, as I when we did the Python to C integration, we did not bother about what type of Python data we pass. We just pass the data which is um, very generic to Python, very specific to Python. Now, in NumPy, though it is also implemented in C, if you pass the same data type that is being used in Python, whatever you do in C, you will not be able to achieve maximum performance. So what is done is, even the data types are modified to suit the C programming world. So when it is compiled and run on a CPU, what happens is, as I explained to you earlier, the Python code is running on interpreter, okay, and then that creates a bytecode, and bytecode is running on the virtual machine, and that is generating the assembly of the CPU, and then it runs. So, and it is again processed or line by line, and then it generates a bytecode, and bytecode is getting executed. Now we will not get better performance by doing this. We so interface all the NumPy libraries in C. That means what happens? It is with the interpreter, the C library also is Python NumPy library is also added, maybe .lib. So when you call some function, NumPy function, it executes the library function. Library is compiled for a particular CPU, so it is executing the CPU's ASM. There is no bytecode generation or virtual machine coming into the play. So a virtual machine is avoided, and directly it runs on the CPU, executing the CPU instructions. Now, when we do this using the C library, we can also do some more optimization to make it faster when it is executing a C library. What is that? Whatever data you pass, if it is adaptable to the C world, in the sense, if you are passing an array, if you pass an array which is same like C array. So if you say int array in C is nothing but integer values, maybe 1, 2, 3, arranged in a contiguous space in memory. Whereas if you are having an Python, if you are having an integer array, it is actually integer objects which are being referred, and then we are maintaining a list of references to the integer objects. So each of them are integer objects. You know that it is all references to the integer objects which is being maintained in an array. So this kind of array, even if you pass it to C, it will not benefit much. So you need to convert, and you need to have some Python data type which are adaptable and useful for C library to function efficiently. So we are going to see some data types which are used in NumPy, which is suitable for C functions. So there are several important differences between NumPy arrays and the standard Python sequences. As I said, it is one important thing is num arrays have fixed size of creation. So you know that in Python, the arrays are also, even if it is list can also be considered as an array. You can easily add more element to this, and we can keep extending it, because the list element, an object, is maintained as again a list of objects. So you can keep on adding it to this. There is no contiguous memory space is needed. Whereas, as I mentioned, NumPy has elements which are all in contiguous memory. Suppose you have created an array of some 1, 2, 3, 4, 5, 6 elements, and then you want to add another element. You cannot append it to this, because in the memory, maybe some other data may be already occupying this area. So if you want to add another element to the array, you cannot do it in a contiguous space, because the num arrays have to be contiguous in memory. What happens in NumPy is arrays are always created in fixed creation at a fixed size. So if you want to modify the size, what happens is this array is copied and then a new thing is added to it. So it is like a string. In Python, string is immutable. Similarly, NumPy arrays are immutable. That means you can, if you want to add to that, you need to, it will be creating a new NumPy array and then it will be adding it. So you have to keep in mind that if your algorithm is modifying the size of your NumPy arrays, you are in fact writing a code which is inefficient. So you have to decide, in case if your algorithm needs the maximum size of something, you have to decide the size of the array well in advance so that you don't need to append it to the list. Though it allows, it is inefficient in terms of execution time. So you have to keep it in mind that your algorithm will, even if you are writing a very good algorithm, if your arrays are keep on changing, the size, number of elements in the array are changing, it's not going to be efficient. So that's why having a knowledge of this is important. So changing the size of ND array is a class I mentioned. So any array that you create is of type ND array class. So if you are changing the size, what happens is a new array is created by deleting the original one, and then a new element is added. Okay, I hope you are clear about what I am saying. So all the elements in NumPy arrays are all required to be of same data type. Now, why do we need this condition? Okay, I understand that we need to have a size which is fixed in NumPy. I explained to you why it is required, because it will not be contiguous space if you increase it later on. So it is copying it and then creating in a new place and then doing it. But why are we giving a restriction that it has to be of same type? I will come to that soon. Hold on. That reason I will give you. And though NumPy arrays are all of same size and they need to be of same data type, that is correct. But one exception to the thing is of object types. They can be of different sized elements. So if you have an array, now when I say same size, see here 3 elements are there. I have only 2 elements here. So now in NumPy array normally, except for this, it does not allow you to have a different sized elements in the array. Okay, even though they are all of the same type, even if you are having the same integers in all, it expects that all of them are of same length. So if you are differing it, size is changing, then you need to have an object type. That we will talk about it later. Okay, now how is it improving the performance? I said that it is implemented in C. That doesn't only limit it. It is, I mentioned also that it has to be in contiguous space. So not like Python list, all the elements are all arranged in a contiguous memory. Now, why should it be of same type? Okay, why can't I have, even though if it is in the same memory, why can't I have an integer and then maybe a float, and then maybe both of them, I'll say that's a float, so 4-byte value. This also 4-byte value. Actually, it occupies the same size. Even then, type should not be same. Why? Because when you are operating on the elements, based on the type of the data, the operation has to be either performed as an integer addition or a floating point addition, right? So if it has to be done, then we need to use different instructions. Suppose if you are doing an integer addition, you may do some assembly instructions which are doing add r1 comma r2 something. Whereas if you are doing a floating point arithmetic, maybe add f floating point r3 comma r4. Now you need to know that the registers which are there are holding an integer value or a floating point value. In some CPUs, the registers itself will be different. So normally integer values and pointers are all in the registers which can be same. Okay, they are same type. Whereas floating point, there are different set of registers meant for the floating point values. So this is a normal CPU. This is a floating point processing unit. So it could be either 32-bit wide or 64-bit wide or 128-bit. It could be much more. So based on the type of the float variable, you may have a different registers altogether, and it will be performing a floating point arithmetic internally. So you need to know what type of data you are accessing it from the memory, even if you are having them in a contiguous space. So The requirement that an array is of same type is important because when it is accessing each element, if it knows that it is accessing only integers or a float, then the instructions which are generated for accessing them and processing them is much concise. Okay, it will be concise and it can be much faster. Whereas if you expect the type to be different, then they will have to check every time what they are accessing is an integer type or a float type. So the code will be cumbersome and it will be inefficient. So they have put a restriction that NumPy is of data type, which is of same type. Now, one more reason is also there. The reason that this NumPy is implemented in C, whatever NumPy arrays you have, they can easily transfer it to an array in C language. So, because you know that integer, even in C also, you have to have the same type of array in C. You cannot have an array of different types unless you have it as a structure and then array of structures. You cannot have a different types in the array element. So it is easily portable to C programming world. That's why they have put the restriction that NumPy has to have the same type of elements in the array. So it will be a good question, interview question, which you can answer if you have the understanding of what is happening underneath. You can say that it is because it is implemented in C and transferring the implementation of NumPy computations and the data elements into C will be easier because there is one-to-one mapping is there, because C also restricts that all the arrays have to be of same type. And then one more thing is it is all arranged in a contiguous memory space so that accessing and processing them is easier, and that is why NumPy restricts that the array elements have to be of same data type. Okay, this will be a good reply if you are asked either in the exam or in the interviews to give you a reason behind this restriction. Now, no type checking will be needed while accessing the each element of an array, thus improving the performance. Because you know that if type checking is not done, that if condition is not there and else condition, jump is not there. So lots of advantages are there if you don't need to check what type of element you are accessing it. Whereas in Python, everything needs to be verified, what object it is. So it will be a double reference. It has to access this array and then it has to access the object, and then internally it has to check the type and then only perform the job. So it is a much more involved. That's why Python computations are inefficient compared to NumPy arrays computations. Having the elements in contiguous space, now I am bringing one more element, SSE. Okay, this is a streaming SIMD extension. Okay, I will talk about it shortly in the next slide. It also helps in implementing it in using SSE instructions of the CPU. Okay, right now I am just not going into detail. I will tell you in the next slide. NumPy is efficient compared to Python implementation because of these reasons. Okay, but these are the following reasons why it is inefficient. Now let us understand what is this SSE all about. That is about vectorization in NumPy. Now everything is a vector in NumPy. Okay, now what is a vector? Now suppose if you are multiplying a matrix or even it's a one single dimensional element, you need to, it's not a matrix multiplication, you are one-to-one, you are multiplying the elements in an array, then you will be performing this many operations. How many operations? 5 operations you will be doing. Whereas if you are doing a vector operation, this is one vector, all 4 elements, and then other 4 elements, they get multiplied. The results are same. Okay, 1 and 6 is only multiplied here. Sorry, I'm not able to see my. Okay, 1 and 6 only is multiplied here, 2 and 7 only is multiplied, but all the multiplications of this is happening in parallel. Now, what do I mean? They happen in parallel. If they happen in parallel, then I can say that the whole thing is one operation. Okay. When I say one operation means, suppose if it is an integer, it's all integer numbers, it's not a floating point number. So the CPU, the ALU might take maybe one clock cycle. Okay, one clock cycle to multiply on 2 integers. Now, if it is a vector multiplication, the processor uses different instruction which is called SSE instruction. I will talk about it soon. Then all the multiplications are done in parallel. That means there is a set of ALUs. There are set of ALUs. Okay, I assume that there are 4 ALUs, suppose. Then what happens is the job that it has to do is multiplication. This is the instruction which is saying that perform multiplication. Now each ALU needs 2 input. Okay, they are coming from A0 and B0 and 1. This is 1 1 2 2. So they are all fed in parallel. So these array elements are fed in parallel, and in one clock cycle the results are out, and then the results are written in a, again the 4 results are coming out. So because it is happening in parallel with the help of a parallel hardware inside, we say that vector operations are performed as a single operation. We call it as a single operation. Reason being, they are all done in parallel, and because of that, we get so much of improvement in terms of time, because the number of clock cycles taken for this multiplication is same as one multiplication here. Here it would have taken, suppose this is taking 5 cycles. This will only take 2 cycles. When I say cycles means, suppose this processor is running on, okay, this is not a clock pulse. Clock pulse should be of always 50 duty cycle. The time of this should be same. So if this is of 1 gigahertz, suppose frequency is 1 gigahertz, what is the time here? This is 1 by f is a time period, which is nothing but 1 by 10 power 9. So it is 10 power minus 9, which is nothing but 1 nanosecond. So one clock cycle takes 1 nanosecond. Here the time taken will be 5 nanoseconds, whereas here it will be just 2 nanoseconds. So this is the improvement that you get in terms of performing a vector multiplication. Now what is that you need? You need a hardware which is capable of having multiple ALUs, and then you need a hardware to provide this kind of a instruction feeding the data, multiple data for a single instruction. So SIMD, single instruction, which is a multiplication operation performed on multiple data, which is multiple data is performed simultaneously. This is called SIMD architecture, and another name for this is a vector processor. Okay, vector processors is also the same like this, because vector processor has multiple instructions coming. Okay, it's a little different. Vector processor may have multiple instructions and multiple data. SIMD is single instruction, multiple data. Okay, so it is a parallelization. A lot of parallelization happens in the execution. So vectorization helps in NumPy by performing a vector arithmetic. Now let me explain that. Now most of the functions are in C, so it executes, instead of Python loops, it executes much more efficiently in C. It speeds up the NumPy code further by using the streaming SIMD extension. Now what I mean by streaming SIMD instruction is the similar instruction that I showed you, SIMD instruction, you need to use different instruction. If you use normal mul instruction, it will not be performed using the SIMD architecture. So you need to use an extension to Intel processor. Intel has an extension to this. So you need to have this kind of instruction generated by the compiler. So the NumPy, when it is compiled and generated using C compiler, it generates SSE instruction. You have to enable that option. Then what happens is your NumPy library runs much faster, provided your CPU has the SIMD architecture built into the CPU. In case if it is not built into it, then even the compiler running on the CPU will know that this CPU does not have the SIMD feature. Then it will do normal multiplication. So you will not get this kind of a optimization if the processor does not support. So you can imagine a Python code running the NumPy library needs to worry about what is the hardware underneath. If you have a SIMD enabled CPU and your compiler also generates the instructions of this type, then all your multiplications are done much faster on that kind of a CPU architecture. Okay, so vector operations are done internally, and moreover coding in NumPy is also simpler. I am sure you might have already seen that. So this is what I wanted to highlight before I show you some code which you might have already been familiar. Um, let me see if there are any questions so far from anyone. Okay. Let me ask you, whatever I explained, is it clear at least at a higher level, or you want me to explain anything in detail a little bit? Okay. Anand Jain is saying others also I accept. There are no questions, so I will assume that you guys are okay. Fine. Now let us look at some code. Okay, I am using Python only. Import. Okay. Now what I want to do is I want to show C code, sorry, Python code as well as normal NumPy code. So let us write it like this. Now what is happening? I am sure you guys know it. So it is a individual objects which are there in the list. Now what if I do NP array, and then I said that we need to use ND array is a array is a function, and then I can pass a to it. I can pass a list to it, and then let me print it. Now what do you expect to happen here? Will it give error, or will it accept it? Or if it accepts, what you get to see in individual element? So let us try to understand this. Okay. So here what is happening is we have an array of element. This is what I am passing it to the NP array. Now it expects that I need to pass same data element, but I have passed it different data types. Since it can promote this element into floating point, let me not say floating point variable, it accepts even if I pass different data types to this NPRA function, and then it actually converts it into float and then prints it. So it stores it. Now this is what has happened: 1.2, 2.0, 1.0, 3.0, 4.0. Okay. Now my another question is, what type of variable is created? Is it a float or a double? Okay. Now let me give you some background on why it is not float. Okay. Is it a type float or a double? Now you know that float is a 4-byte value and then double is 8 bytes value. Now I have not mentioned anything 1, 2, 3 and 4.0, and I have not given any D type, anything I have not given. So it has to default, it has to assume if it is 4.0, I need to convert everything to float, but it has a option either to use a float or a double. Now if you know, I think I mentioned it in the Python class, in C what happens is, if I define define pi as 3.14 and then I write a double D, okay, not double, if I say even float, what happens is all the constants what I define in C, they are default assumed to be double in the case if I am having a decimal value. So similar to that, they follow the same convention here. If I have no type defined, then the values are stored as double. Now how do you verify it? Let us see that one by one. Now let me first show what is the type of NPA. what do you expect? It should be in NumPy ND array. Okay, as I mentioned that is a type of ND array. Now, what is the dimension? Dimension of NPA. So, because it's a n dimensional array, is n dim, it is 1. Now, what does that mean? It's a single dimensional array element. So, because it's itself an array, n dimensional array, any element, a vector element, is also a one dimensional array. This is a one dimension. I'm sure you are aware of it. So it's a one single. Number of elements are different, but there is only one array of element. Now, what is the shape? Now, another thing is shape. Shape of NPA is now you know that. Okay, now I don't know whether I can ask you guys, why is it there is a one comma here pending? Okay, why is there a comma? I don't know whether I mentioned it in Python class. Let me explain it maybe. See, some element 4 comma is there. It means that this is of type tuple, because you know the tuple is parenthesis, and if I have an element here, if I do not have a comma, then it can be interpreted as just a parenthesis I have given around number value 2. So this is different from this. This is just a value 2 and this is a value which is inside a tuple. So now what is happening here is, what is getting printed is 4 comma this, that means 4 elements are there, so I am getting shape as 4, but it is giving a comma to say that what this function, whatever this is returning a tuple. It is returning a tuple with the dimensions of number of elements. Okay, let me write it. It returns a tuple with integers ins giving the number of elements in each dimension. So it's a single dimension array. So only one entry is there. If there was a two-dimensional array, then you would have had another element. Then you would have easily known that it is a tuple type with the values. So I hope this is clear. I don't want to show you. You can try it out by doing it. Now print size of the array. Size of NPA. You can say that it's size. Now, does it return the size in terms of bytes, or does it return the size in terms of elements? So you can see that it gives you 4. It's a number of elements in the in the array, ND array. So it is a 4 element. Now I mentioned that it has a data type. What is a data type? Let us see that it is whether double or float. Now data type of elements in NPA. So D type is the data type. Is a float 64. Now what they have done, they didn't like the C, where C always says that float is 32 bit and double is 64 bit, and they don't want to have that confusion. So float 32, float 64. That is what is defined in Python or in NumPy. To be specific, this D type is a type data types defined in NumPy package or library. So it defines it as a float 64. That means 8 bytes are there. Now, if you want to know what is the total size of each element. Now, first of all, let us find out the element type. memory size of each element in NPA. What is that? NPA item size. So what do you expect? It should be 8. So each element is occupying 8 bytes. So total size of this array is, I am sure you know, total size of NPA in bytes is, you need to do NPA dot size into NPA dot item size. So that will give you what is the total size of this particular array. It occupies 32 bytes. Now, as I mentioned, it will be occupying 32 bytes of contiguous memory, that you have to remember. Okay. Now, let us go into maybe two-dimensional array. Let me create 2 rows, 3 column. I am passing Python. Okay. Now, this is okay. I am constructing a Python list only. I don't need this anyway. Now let us construct a NP array. Just for completeness sake, I have put np.nd, sorry, array a two comma 3. Okay. Now printf. Okay. This gives you this anyway. You know it. Let me. In case you have any question, please tell me, because I am not watching the messenger. Okay, now let me, what do I do if I have to append it? If I want to, as I mentioned that we need to have, if you want to create a new array, it creates a, totally it copies it and then creates a new array. So NP, I want to make it 3 comma 3. That means I want to add one more element, a row, one more element, a 3 comma 3 3. Then what do I do? NP dot append NPA23. I am giving the original NP array. So let me show you this function, what it accepts. I'm sure you might be knowing it. So it is like append is, you pass the original array and then pass the new values what you want, and then axis, you know, where you want this new value to be added. Okay. Axis is the number of each array element. Is axis equal to 1 means it is doing it in the row wise. Then what happens is it creates a new array, a copy of array with values appended to axis, a copy of array. That means it is creating a new array and then it copies the new values. And if I don't mention any axis, it flattens the array. So flattens means it will open up all the elements and then gives you a individual element. So now let me show you 7 8 9. I don't give any axis. Then print npa 2, oh sorry, 3. Okay, I should not write 3 comma 3 because it is not going to be 3 comma 3. npa, just I will write npa. Now what happens is flattened out, because I have not mentioned axis, it flattens out. So if I want it to make where is copy? I need to give axis. I'm sure you must be knowing this. So I don't know whether I should do all this or not. Axis 1 or axis 0. It should be axis 0. So you can, oh sorry, what did I do? Yeah, if I don't pass it like this, is wrong because it expects that object has to be passed inside an element. You have this added to the end of the array. So you see that it is 3 by 3. So I can make it 3 by 3 now. Okay. Now, if I want, I can, we'll go into the details later on. Now, any other questions you have so far? Anything? I think you are already aware of all this, hopefully. What I thought I will explain you about internal details of NumPy now in this first lecture. Any other questions you have on what I explained so far? Okay, maybe if there are no questions, I will just explain one more thing and we will stop. Object I mentioned, I am sure you guys may be knowing it. Let me copy this. Now, will it accept? Oh, okay, I have to do it. Now, first I will let me create a n2x and then I will do it. So I'm just creating a list first, and then I want to create np array. Will it allow? So it doesn't give you, you cannot do that because it only allows if d type is of object type. Now what do I do? If I need to create it, then I need to have a one more, and then I have to mention that it is of object type. Now what happens if I do that? Let us see that. Does it allow? It allows. Only thing is it is of object type. All the elements in this are converted into the object type and then they are passed on. So it doesn't bother about number of elements in it because this is going to be an object and this is also going to be another object type. So it allows you to create a NumPy array of type object but not of any other type. So this is the one which I showed you in the where are they? Here. So this is what I showed you earlier. So that's the reason only this type is allowed to have different dimensions. Okay, different sized elements. Okay, fine. So any questions so far? Now what I will do, we will continue on NumPy maybe couple of classes. I'll go little, give you some more other examples. Then we can go into TensorFlow later on. Okay, after this, maybe we'll do some few exercises also in the lab, in the coming lab on NumPy. Anything specific? I don't know how much of NumPy you have guys have done. So you can tell me whether we need to do more. You want me to go deeper? What do you want to do? You give me some suggestions. I can do accordingly. I don't know how much of NumPy you know. Okay. So I will do some optimizations or some different ways of doing NumPy arithmetic. I will go into that deeper level, not simple programs I will not do. Okay. Okay, some basics in ML. Okay. So maybe I will bring out all the no unknown things which are there in NumPy. Maybe implementation details little bit. Okay. Fine. No issues. Okay, guys. So we will stop here.